So in this video we're going to look at the matrix form of a system of linear equations. So here's a system of three equations in three unknowns, and we've already looked at how to solve this type of an equation and interpret the results using Gauss-Jordan elimination and an augmented matrix. However, there's going to be another way that we can approach solving a system of equations that will be particularly of particular interest, more from a theoretical perspective, especially when the solution is unique, and it also allows you to determine when there isn't a unique solution. So what we're going to do is introduce the matrix form of a system of linear equations as kind of an alternate approach to solving a system. And so here's the basic idea. And this will work for any m by n system of linear equations, m equations and n unknowns. Here I'm doing a particular case where it's three equations, three unknowns. And the idea is that we can take the left-hand side and put it into a matrix. So I can take the 2x sub 1 plus 3x sub 2 minus x sub 3 and put it as a single entry in a matrix. And then I can take the second equation, x sub 1 minus x sub 2 minus x sub 3, and put it as a single entry into a matrix. And then the minus x sub 1 minus 2x sub 2 plus 3x sub 3 as a single entry into a matrix. And then set it equal to the matrix of constant terms, 2, 7, and 5. And in this case, this matrix has 3 rows and 1 column because these 3 pieces are a single entry into this matrix. So this is a 3 by 1 matrix that's equal to a 3 by 1 matrix where clearly the first row is equal to 2, the second row is equal to 7, and the third row is equal to 5. And that just comes straight from interpreting what this system means. And the idea is that this matrix on the left-hand side can be rewritten. So on the right-hand side, we'll keep the matrix or column vector of constants unchanged. And over here, we want to identify that if we take the matrix of coefficients, so 2, 3, negative 1, 2, 3, negative 1, and then 1, negative 1, negative 1, 1, negative 1, negative 1, and negative 1, negative 2, 3, negative 1, negative 2, 3. So we take the coefficient matrix, which is a 3 by 3 matrix, 3 rows and 3 distinct columns. If we multiply it by the column vector that contains the unknowns, x sub 1, x sub 2, x sub 3, which is a 3 row by 1 column matrix, the product is possible because the 3's match, and the product when we take it is going to be a 3 by 1 matrix, which is what we started with up here. And if we look at the matrix multiplication that's going on here, what we'll see is that this product gives us back what we started with. So when we multiply matrices, we take the rows dotted with the columns. So this would be row 1 dotted with column 1 would be 2 times x sub 1 is 2x sub 1, plus 3 times x sub 2 is plus 3x sub 2, minus 1 times x sub 3 is minus x sub 3. The second row dotted with the first column would give us 1 times x sub 1 is x sub 1, minus 1 times x sub 2 is minus x sub 2, minus 1 times x sub 3 is minus x sub 3, and finally row 3 dotted with column 1 is going to be negative 1 times x sub 1 is minus x sub 1, minus 2 times x sub 2 is minus 2x sub 2, plus 3 times x sub 3 is plus 3x sub 3. So the idea is that this product, this coefficient of this matrix of coefficients times the column vector of unknowns or variables equal to the constant terms is exactly the same as what we had on the previous line. So this gives us then an alternate way to represent this system of equations. And what we want to notice is the form of this. The form of this is that we have a matrix of coefficients, which is pretty customary to call it A, times the column vector of the variables, x sub 1, x sub 2, x sub 3, equaling the matrix of constants, which we call B. So in general, the matrix form of a system of linear equations is the form that we get when we write it in this form right here. And this form looks like AX, a coefficient matrix times X, where X is the column vector of variables, equal to B. So this form here is the matrix form of a system, and any m by n system can be written in this format. So this form is going to be of theoretical interest, especially if A inverse exists, because if the inverse of the coefficient matrix exists, which it may or may not do, it might not exist, but if the coefficient matrix A does have an inverse, then if we multiplied both sides by the inverse, so A inverse times AX equaling, I multiplied A inverse on the left-hand side, so I have to multiply A inverse on the left-hand side of the B over here. I can't write B times A inverse. Well, A inverse times A just equals the identity matrix I times X equals A inverse B, and the identity matrix times X will just equal X, because remember, the identity matrix acts like the number 1 does in the real numbers. And so it'll turn out that if the inverse exists, what we're going to find out is that the solution is going to be unique, and it's going to equal A inverse times B. And remember, when we have a system, the solution is either unique, or there's no solution at all, or there are infinitely many solutions. We never get a case where there's just 2 or just 3 solutions. That doesn't happen. So this form is going to be of some theoretical interest, and in the next video we'll start to develop working with systems of equations written in matrix form.